Okay, we carry on with paper 3 2019, and this is part B, question 4. Dettol contains other chemicals including alpha terpineol, which is shown below. Right, it's a chiral compound, and the first thing we need to do is show with an asterisk the chiral center. Now you remember that the chiral center is a carbon that has 4 different groups hanging off it. So if we look at this one, this group, this group, this group, right, and the hydrogen, they're all 3 different groups. Right, so that's our chiral center there, and we would mark that with an asterisk. Okay, moving on to part 2. Alpha terpineol meets the requirements for EZ isomerism. However, only one EZ isomer exists. Okay, that's fine. So explain why it meets the requirements for EZ isomerism. Well, it's got, let's put the answer to this up here. So it's each carbon, right, in a carbon-carbon double bond, all right, is attached to different groups. And going to the next question, this one, whether it's an E or a Z isomer. Well, if we look at our 2 carbons in the double bond, we've got this carbon compared to this carbon. This is the higher priority, and we've got this carbon compared to the hydrogen, so that's the high priority. So the 2 high priority groups are on the same side of the double bond. So it's a Z isomer as the high priority groups, on the same side as double bond. Like that. And lastly, why only one EZ isomer of alpha terpineol exists? Well, if you look at the high priority groups, they're in a ring, and so if you wanted, say, this carbon to move over there for it to be an E isomer, you would break the ring. All right, so you say both priority groups are in the ring, otherwise the ring would break. Or probably better to say the ring locks the high priority groups on one side of the double bond. Like that. Moving on to part 3, alpha terpineol, which we've got down at the bottom here, contains 2 functional groups. Here's one functional group, it's the double bond. Here's another functional group, which is the hydroxyl group. So for each functional group, choose a reagent that reacts with that group only, and draw the structures for the organic products of the reactions. So we want a reagent that reacts with a double bond. Okay, so we're going to have bromine is the usual one, and we describe that functional group as an alkene or a cycloalkene, and let's just draw it out. So we're going to have a bromine on each of those carbons, and the rest is the same. Notice we've got bromine, so it doesn't substitute with the hydroxyl group. If we had bromide, it would do, which is what we can use in the next one. So the other functional group is the hydroxyl group, and course it's an alcohol, but let's have a look. This carbon here, right, is attached to 1, 2, 3 other carbons, so it's a tertiary alcohol. And the functional group that reacts with it, there's a few we could choose, but bear in mind that we have to draw the organic product. So why don't we just choose a substitution reaction with, say, potassium bromide, so KBr and then we can draw out our product. Like so. We could, of course, alcohols, of course, would react with acids to make esters, but the esters would be trickier to draw, so let's not. And there you have all the marks. Okay, moving on to question 5. We have another practical question here, which is the determination of an enthalpy change with Hess's law type question, standard type question. And we've got copper sulfate and sodium thiosulfate. And first of all, we're going to work out the enthalpy change of hydrating some anhydrous copper sulfate, as in this reaction here. Okay, so I'll let you read the question so that I can get on with the answer. So if you need a few minutes to read the question, pause and come back. All right, so the first question is calculate the enthalpy of solution for anhydrous copper sulfate. And determine the enthalpy change of the reaction. And show an energy cycle linking the enthalpy changes. Okay, 6 marks. So let's look at these reactions. We're getting aqueous copper sulfate here and aqueous copper sulfate here. So both the same thing. So they're going to be the bottom of your Hess's law triangle. And this reaction here is going to be the top of your Hess's law triangle. So let's draw it out then. So we've got copper sulfate anhydrous, right? We're going to add a load of water to it, or just enough water to it to make hydrated copper sulfate, the blue crystals that we're familiar with. All right, now solid. So that means there's no excess water. All of the water that's been added here has gone into the crystal structure. All right, so this is very difficult to do accurately on its own, because how do you know how much water to add such that you don't get any either excess water making some solution, or too little water meaning you've still got some anhydrous copper sulfate left over. Right, so for that reason we do it indirectly and use Hess's law. And so this reaction is when we add water to anhydrous copper sulfate, and we get copper sulfate solution. Right, and that is when we do the same reaction, except we start with hydrated copper sulfate instead. All right, and we've got plus aqueous there. Okay, so what the question demands is that we work out this enthalpy change of that reaction. That's the enthalpy change that's underlined here, right? And we also have to work out the enthalpy change of this reaction here. This is 5.1. This one here. It's the other way around, sorry. So we have to work out the enthalpy change of this reaction here, where which is experiment 1, and that allows us to have 2 out of 3 legs of the triangle, so that we can get the enthalpy change of solution of copper sulfate. So down here at the bottom, we're told that for the other reaction, right, in experiment 2, right, which is the right-hand leg of our triangle as we look at it, this is plus 8.43 kilojoules per mole. So we're told that one, and this one here, let's call the left-hand leg. All right, that we're going to work out using Q equals mc delta T. All right, so let's draw a little subtitle. Just write in, this is reaction 5.2, this is reaction 5.1, and let's draw a little subtitle. Work out reaction 5.2 first. Yeah, so we're going to use Q equals mc delta T, and these two gives us delta T, and this is the mass of water that we're heating up, right? So this is going to give us M, right? And this is going to give us the amount of anhydrous copper sulfate that we've got. So this is going to give we're going to use that to work out what moles is. So we've got that equation, so we can say where, right, the M equals 74.13, take 23.43, so when we substitute in that and C and delta T, so delta T is 13.5, and this comes out at 50.7. Right, we substitute in those 3 values, 4.18 for C, we get 2861 joules. Right, joules because we were using grams, and we can convert that straight away to kilojoules, so that's 2.861 kilojoules. Alright, that's using the quantities that we were given in the question, but if we now want to work out the enthalpy change, we have to work out per mole, and you can see from the temperature increase that it's an exothermic reaction, so we're going to put a minus in there in our equation to find delta H. Right, so we've got minus 2.861. We know that already, and we have to work out moles. So let's just work out moles first, so we can put a little semicolon and where moles equals. Okay, so moles is going to be mass over MR, and our mass of stuff is 28.04 minus the empty bottle 20.06. Alright, so that's going to give us mass, and MR for our copper sulfate solid is 159.6. So moles comes out to be 0.05. Keeping our 3 significant figures like that. Therefore, going back to delta H, so that's going to be minus Q, so that's minus 2.861 divided by 0.05, and that gives us 57.22 minus 57.22 kilojoules per mole. And that gets us the answer to reaction 5.2, but we're still asked for the enthalpy change of reaction 5.1. right? So then we're going to go back to our Hess's law cycle. So let's just put delta H 5.1, save us right now. So copper sulfate. That's going to be, let's just draw a little arrow in here like so, so that we can see that the indirect route that we're taking, the blue arrow, goes with the first arrow, the 5.2 reaction arrow. Right, so we can keep the sign of that enthalpy change the same, which is minus 57.22. And now you see the blue arrow is going against the enthalpy change for reaction 5.3. So we have to change the sign of that, right? So it's going from plus 8.43 to minus 8.43. All right, so that turns out to be minus 65.65 kilojoules per mole. So there you have those marks there. So moving on to part 2, about uncertainties in the reading of an instrument, in this case a thermometer. Right, so we've got a reading each time we use the thermometer. We've got an uncertainty of plus minus 0.1 degrees C, and we calculate, right, or the student calculates a 20% uncertainty, and we need to work out the temperature change. So I'll use the space on the right here. The usual equation is the percentage, right, uncertainty right, is the number of times you use the instrument. Now we've got a initial and a final temperature, so we're using the thermometer twice, times the precision of the thermometer, which we're given there as plus minus 0.1, and that's the numerator of the equation, and the denominator of the equation is your actual, in this case, your delta T, your difference between your two temperature readings, right, which is what we're being asked for. Calculate the temperature change in experiment 2. Right, so that's the equation, and we know that that is 20%. All right, so if we've got to multiply that by 100, make it a percentage, and then the answer is 20. So all we have to do is rearrange this. Okay, so delta T, right, is 2 times 0.1 times 100 over 20. Just using algebra to rearrange that, cross multiply, and so 2 times 0.1 is 0.2, times 100 is 20, so 20 over 20 is 1, all right, and so it's 1 degree C, all right. Probably only got one significant figure, so we'll leave it there at 1 degree C, like that. Okay, yeah, moving on to part B. So now we're got this different reaction, sodium thiosulfate, and we've got free enthalpy change. So I'll let you read the question there, and you'll realise that the equation that we're going to use, I'll just draw a line under that, make it clear. The equation that we're going to use here is delta G equals delta H, take T delta S, and we're being asked for the standard entropy, right, just S, so not delta S, just S, of anhydrous thiosulfate, right, so this one here, entropy of that one. We're given the entropy of water, and we're given the entropy of hydrated sodium thiosulfate here and here, all right. So when we come to work out delta S, we've got 2 out of the 3, all right. So if we knew what delta S is, then we could work out what the standard entropy of anhydrous sodium thiosulfate was. Okay, so how do we get delta S for the reaction? Well, we rearrange the equation, all right. So we're going to have delta S is delta H take delta G all over T in Kelvin, right, and we're all at standard conditions here, so T is 298. Delta H and delta G we've been given, and they're both in the in kilojoules. All right, so delta H is minus 55.8, delta G is minus 16.1, T is 298. You put those three values into the equation and you get minus 0.133 kilojoules per Kelvin per mole. Right, but you notice our units in the table here are joules, right? So let's have our delta S in joules as well. All right, so that's minus 133 joules per Kelvin per mole. All right, now so now we need a second equation. We need the equation for delta S. All right, so delta S equals the sum of the entropies of the products. Take the sum of the entropies of the reactants of the reaction we're considering. Okay, so there is only one product, hydrated sodium thiosulfate, and we are given the entropy of that. All right, so we got 372.4 is that number there, and we've got two reactants. We've got water and we've got anhydrous sodium thiosulfate. So the anhydrous sodium thiosulfate is the S that we want, right? So we can just call that S. Let's just call it S. And the entropy of water, standard entropy of water, 69.9 per 1 mole, right? But we've got 5 moles, so we have to multiply that up by 5. So that's 69.9 times 5. All right, and delta S we just calculated as minus 133. Like so. Okay, so we've just substituted in all our numbers with our one unknown, which is our S here. Right, so if we rearrange for S and solve, then we get a value of S to be, comes out 156, right? So all entropies have to be positive, of course. So if you get a negative number, something's gone wrong. Check your answer. And let's put our units in there, joules per Kelvin per mole. Right, so there you have those marks. So part C is about bond angles and shapes of molecules again. So this time we've got the thiosulfate ion, and we've got the displayed formula there, and it wants us to predict the bond angle of the OSS bond angle. So that's this bond angle here, and the shape of the thiosulfate ion. Okay, so the central line is this sulfur here, right? So let's count the number of bonds it's got. It's got 2, 4, 6, and it's got 6 outer electrons, so it's got no spare electrons and therefore no lone pairs. All right, so we can consider the double bonds as single bonds, and we know there's no lone pairs. All right, and there's essentially 4 bonds there. So 4 bonds and no lone pairs means a tetrahedral shape. All right, so the easiest thing to work out first is the tetrahedral shape. So the shape is tetrahedral, and then because we've got a standard tetrahedral shape. All right, so we just put 109.5 degrees in there as our bond angle. So that's this mark here. And now in part 2 we're going on to the tetrathionate ions, S4O6 2-, which is a dimer of thiosulfate. Right, so now we have to draw the displayed formula for the tetrathionate ion. And how you can think about this is so notice that we've got a minus charge on this sulfur and a minus charge on the oxygen here. So if we drew another atom, let's draw it just as another one as it's drawn, right? So we've got O-, right, bond, sulfur, oxygen, sulfur minus, double bond, oxygen. If we drew that, we've got these 2 electrons here, all right, that could just, instead of being lonely electrons, they could operate as a pair and be shared between the sulfur and the oxygen, so form a covalent bond like that. And it could happen like that, or you could have drawn, you know, this new ion the other way around and have a sulfur-sulfur bond as well. But let's draw it out neatly as I've written it above. Right, so you've got the oxygen with a 1- charge, and you've got the sulfur, right, with a couple of double bonds to oxygens. You've got the first sulfur. Now you've got a new covalent bond, in this case to an oxygen, and then we've got the rest of the second ion. And dimer, that's the dimer, right? So di as in 2. Okay, question 6 is about transition metals and their reactions. We've got a flow chart here, and we're going to work out what A and B are. We start with iron 2 sulfide, so that is just simply FeS, right? And we're going to dissolve that in acidic solution, and we get the iron aqua complex, which is, and the iron is still iron 2+, and it's pale green. Okay, so on the way to A, because we've got to identify A, let's follow the path down to it, because we're going to have to do the rest anyway. So if we bubble some chlorine gas through it, what's going to happen? Well, the clue is orange-brown, right? Because the orange-brown gives us, and it's a solution, so we must have iron 3+. So the colour gives us the clue that we've got iron 3+ ions now in solution. So the chlorine must be acting as an oxidizing agent, right? So we're going to have Fe. We're going to have it's still a hex aqua complex, right? But it's going to be 3+ now, because our iron has been oxidized by the chlorine. Okay, so that's what we've got there in that orange-brown solution box, and then we add some sodium hydroxide to it. So hydroxide ions, of course, are going to act as a base, and they're going to rip protons off these 6 water molecules. Sorry, at least 3 of the water molecules, to precipitate out iron 3 hydroxide. Right, so we can write that in there. Right, so once we've got 3 hydroxide ions, we've neutralized the charge on the 3+ iron, right? So that becomes a solid and therefore a precipitate. So we've written the formula of A there. So now let's move on to B. In this first reaction, we've made our hex aqua iron 2+ complex. We've also made some hydrogen sulfide, and when we react that with silver nitrate, we're going to get some silver sulfates, silver sulfide rather. So it's a precipitate, and it's got this smaller mass here. So silver, as you know, is a 1+ ion, and when it's in silver sulfide, the sulfide is going to be a 2- ion, so we're going to need Ag2S. That's our proposal, right? So then we just check the ARs 2 times the AR of silver and sulfur makes that formula, just to check that we're correct, and it turns out we are. And in part 2, the student thinks that the reaction of iron sulfide with acid is a redox reaction. Explain why, with reasons, whether the student is correct. Okay, so this is Fe2+, right? And the water molecules are neutral, so the complex also tells us that we've still got iron 2+, right? So the student is incorrect. Because redox reactions require a change in oxidation number. So the reason is as oxidation numbers stay the same. You could say of iron, right, stays at +2. Okay, there we have that. And moving on to part 3, which we've mostly done. Let's write out that equation. So our hexa-aqua ion complex has reacted with chlorine gas. Might as well put state symbols in there. Right, and we know we've got an orange-brown solution, right? So we've got still hexa-aqua, but we've got 3+, right? And the electrons that were with the iron ions are now with 2 chloride ions. And just to balance it up, we need to have 2 iron ions, right? Because we've got 2 chlorine atoms, right? So we need a 2 there and a 2 there. And in part 4, we're going to construct an equation for the reaction of hydrogen sulfide with manganate, which we know, acidified manganate, which we know is a powerful oxidizing agent. All right, so that's going to oxidize our hydrogen sulfide. And what's it going to oxidize into? Well, the clue's here, yellow solid, right? So that is sulfur. So that's a redox reaction. So when it says construct, that's another little clue there that it's not just a simple balancing act. We have to do a redox equation here. All right, so let's start off with our oxidation reaction. Start off with our oxidation reaction. What's being oxidized? Our hydrogen sulfide is being oxidized, and our manganate is our oxidizing agent. Right, so we've got H2S on one side, and we know it's being oxidized. Let's give myself a little bit more space. It's being oxidized into sulfur. All right, so then we follow the normal process of balancing our non-hydrogen and oxygen atoms. Well, we've got 1 sulfur on each side, so that's fine already. But we balance our hydrogens with hydrogen ions, so we need to put 2 hydrogen ions on the right-hand side. And oxygen is nowhere, so that's fine. Lastly, then, we have to balance our charges, so we have to put a couple of electrons on this side to make that neutral, because the left-hand side is neutral. Right, so for now that will do. And now let's think about our reduction equation. We're going to leave a little bit of space. Let me leave a little bit more space than that. So our reduction equation. So if manganate is our oxidizing agent, it is being reduced itself. So MnO4 is being reduced, and it tells us in the question what it's being reduced to, Mn2+ ions. Okay, and following the normal process, we've got 1 manganate on either side, so that our non-hydrogen oxygen atoms are fine already. And we've got 4 oxygens on the left-hand side, so we need 4 water molecules on the right-hand side. Right now we've gone and unbalanced our hydrogens, so we need to put in 8 hydrogen ions on the left-hand side. Now we've gone and unbalanced our charges, so on the left-hand side we've got 8+ and 1-, so that's 7+. Whereas on the right-hand side we've got only 2+. All right, so if we put in 7 take 2 is 5 electrons on the left-hand side, then that would be a good half equation. All right, so next we're going to add them together, right, so that the electrons can cancel. All right, so we've got 2 electrons in the oxidation reaction, and yet we've got 5 electrons in the reduction equation, so we have to multiply our oxidation reaction by 5, and we have to multiply our reduction reaction by 2. All right, and so then what we get is 5 hydrogen sulfides, going to give us 5 sulfurs plus 10 hydrogen ions plus 10 electrons. All right, that's the multiplied up version of it. And when we multiply our reduction equation by 2, we're going to have 2 manganate ions. We're going to have 16 hydrogen ions. We're going to have 10 electrons, and we're going to have 2 manganese 2 plus ions, and we're going to have 8 waters. Okay, so now let's do a little bit of cancelling. So let's look at hydrogens first. So if we, on the right hand side of the oxidation reaction, we have 10 hydrogens, right? But we can cancel those and leave these as 6 hydrogens. Our 10 electrons on the left hand side of our reduction equation cancel with the 10 electrons on the right hand side of our oxidation equation, so that's also good. Anything else cancels? I think that's it. So let's see what it looks like when we write it all out. We're going to have our 5 hydrogen sulfides. From the oxidation reaction, we're going to have 2 manganate ions. We've still got 6 hydrogen ions left over. Right, and on the right hand side, we're going to have 5 sulfurs. From the oxidation reaction, we've got 2 manganese ions, and we've got 8 waters. Right, and that is the answer to part 4. Now, just checking the mark scheme. The mark scheme has got, instead of 6 hydrogens, it's got 16 hydrogens. But I don't see how it can, so I think it must be a mistake in the mark scheme. But if you can justify 16, I'll be interested. So please let me know. Okay, last question. So we've got this compound C, which is a pretty complicated looking ionic compound. And it's hydrated, right? We're told it's hydrated, so we're going to have some of these hydrogens, some or all of these hydrogens, and some or all of these oxygens are going to be in water molecules that are hydrated in the crystal lattice. Right, now stage 1, the student gently heats 0.03 of compound C to remove the water of crystallization. Right, so it tells us that 0.486 grams of water is collected, and we've got 0.03 of anhydrous D. Okay, so that the fact that we've got 0.3 here and 0.3 here means that we've got only one ion in D. So let's work out let's work out how many moles of water we've got. All right, and the reason we do that is to work out the formula of D in the end. Okay, because C, we can say C is D plus hydrated with X water molecules. Right, so we're going to try and find what X is. Right, and if we know what X is, we work out what D is because we already know what C is. So that's what we're going to do. So moles of water, all right, that's what we can do first, is mass over MR. So we've got 0.486 grams over 18 is the MR of water, and that comes out at 0.027 moles, 0.027 moles of water. And that is associated with, that is crystallized with 0.003 moles of D. Right, so we could write out the formula of C like this. We could say, right, D is 0.003, and dot for our coordinate bonds, X is 0.027, right, water molecules. Okay, but they're crazy numbers, so what we're going to do is we're going to divide both by the smaller one, right, and that gives us 1D, right, and 9 water molecules, right, so we know X is 9, right, and so now we can subtract 9 water molecules, or 18 hydrogens and 9 oxygen atoms from C, right? So C then becomes, all right, still got an iron in there. All 18 hydrogens are in the water crystallization, all right, but none of the nitrogens are. So we've still got 3 nitrogens in C, and we've still got 9 of the still got 9 of the oxygen atoms. I'm just pausing because I'm actually working out what D is, not what C is. All right. So apologies for that. So that is what D is, right? And C is that plus the 9 waters. Okay, so good. We've got now we've got what D is, and we've got what C is. Okay, so just remind ourselves that we've got the empirical formula of C up here, but it wants the molecular formulae of C down in the command line. But we know that because we've got 0.3 here and 0.3 here in stage 1, we know that there's only one iron, right? So C we can write out like this. So it's, in fact, a better way of writing out D is going to be iron nitrate, like so. You see, that's makes more sense. And so then we can write out what C is. Is D, right, plus our 9 waters in the crystal structure. Okay, so we've done C and we've done D. So moving on to stage 2 now, we've got compound D, all right, so we've got iron nitrate, right, and we're going to strongly heat it, decompose it. It forms a solid oxide of E, all right, so here's our clue. Our clue is the MR, all right, so that's quite a big MR. It's too big for iron 2 oxide, so it must be Fe2O3. All right, so let's just check. We've got iron's about 56. So 56 times 2 is 112. Oxygen 16 plus 48. All right, 112 plus 48 is 160. All right, cool. So we know that we're going to get iron oxide, iron 3 oxide out like that. All right, so we need 2 of those. All right, what else are we going to get? All right, we don't know. We're going to get 2 gases. Yeah, so let's just write them as F and G so far. All right, so anyway, this is compound E. All right, so now we've got compound E as well. We'll just give that a tick. We can write them out neatly in a minute. So let's look at more clues. So looking at some more information then, in stage 3. In stage 3, we've got students cooling the gas mixture, right, and we've got gas F condenses into a liquid, and we're given the mass of that liquid. Gas G remains a gas, we're given 54. Right, gas G tests, relights a glowing spin. Okay, so G is oxygen. G is oxygen because of the lighter splint. And so the remaining gas to get is F. All right, so let's try and work out the MR of F, because we've got a mass of F, and from these 2 volumes, 270 and 54, we could work out the moles of F. All right, so let's work out moles of F first. Moles of F is going to be the volume, so that's 270 minus the volume of oxygen, is 54, over our 24,000, because it's RTP. All right, and that gives us 0.009 moles. Okay, so now we can work out the MR of F. So MR is mass over moles. Mass is 0.414. Moles is what we just calculated, 0.009. And that comes out at 46. It comes out at 46. Okay, so that will identify our gas. We know there's nitrogen in there. All right, so let's put 114 there. Let's try nitrogen dioxide. So that's 14 plus 32. That works. All right, so F is nitrogen dioxide. All done, 6 marks.